Welcome to the lecture series on Smart Grid, module number 2 from unit number 2, that is Smart Substations. In this module, we are going to cover the Smart Substations, Substation and Feeder Automation, application for monitoring, protection and control. So let's understand first of all the substation. As we know, the substation, the network node where the electric power flows through several substations at different voltage levels on its way between the bulk power stations and end consumers. The network at the transmission and sub-transmission level are always mesh operated. The substation performs the nodes of the mesh network and they connected two or more transmission lines. The simplest case is when all transmission lines have the same voltage. However, typically, the substation performs voltage from high to low and low to high. Substations may perform any of several other important functions like voltage control, reactive power control, power factor control correction, then power flow control by phase shifting, transformers or power electronic plants, UHV, EHV or HVDC conversion to connect high voltage DC lines, connection of two unsynchronous power system by UHV, EHV or HVDC coupling. Substation may perform the other important functions like voltage control, reactive power control or power factor correction, then power flow control by phase shifting transformers or power electronic plants, UHV, EHV or HVDC AC conversion to connect high voltage DC lines, connection of two unsynchronous power system by UHV, EHV, HVDC coupling. Now let's understand the control and automation into the substation with digital technologies. Control and automation of power system by digital technologies. The power system protocol is performed in four-tiered bottom-up hierarchy. So first is process control at the process level. So the process level binary status signal indicates, for example, the position of the switchgear or the transformer tap changer. Analog measurement data, that is voltage or current, are available at the interface of the instrument transformer. Then binary output commands are set for the control of switchgear, tap changer, and various equipment for protection, automation, or auxiliary needs. Analog target values may be set to change the behavior of regulation facilities. Example, the target values for voltage can be set to the transformer voltage controller. So understand the process level. Binary status signal indicates, for example, the position of the switchgear or the transformer tap changer. Analog measurements are nothing but data from the measurement of voltage or current available at the interface of the instrument transformer. Binary output commands are set for the control of switchgear, tap changers, and various equipment for protection, automation, or auxiliary needs. The analog target values may be set to change the behavior of regulation facilities. The large value for voltage can be set to the transformer voltage controller. The next level is the bay level. It is equipped with intelligent electronic devices which provides the interface of the process data acquisition. The conventional way of the data exchange is their acquisition or provision on parallel input-output contacts for binary and analog values of IDs at the bay level. Consequently, each data needs its own wire and contact. The binary data is provided as DC signal at 24, 48, 60, 110 or 220 volt DC. The selection of rated DC voltage depends on the practice of the network operator. The DC voltage is available in separate and mainly redundant DC networks supplied by storage batteries. The batteries are extremely and permanently charged from the auxiliary AC networks. The analog measurements values are acquired as instantaneous values normally sampled in the register of 1 millisecond. Special disturbance or transient recorders may offer a significantly higher sampling resolutions. The bay level ID performs two main tasks: bay control and processing of basic data for the substation automation system and data exchange with the substation control level. Protection of the bay related network assets against stress and damage causes by disturbances and critical state conditions, that is overloading or overvoltages. All signals received from the process are evaluated in the protection and bay control devices. The process data can be visualized in device screen on local request and used in programmable logic to start special automation program communicated to the upper level of the substation control. The bay devices calculates the primary RMS values of instantaneous voltage and current measurements and build associated values like active and reactive power and the power factor cos phi. Only the primary RMS values are locally displayed and transferred to the substation level. The exception is fault record representation, the graphics of instantaneous values before or during and after a build after a fault which can be displayed at the substation screen. The status signal of switch device make it possible to display bay topology and to perform the interlocking functions, blocking and operating of the isolators if the circuit breaker is in status on and of the ground switch if the feeder is under voltage. Appropriate command and impact signals for the process can be performed in the following ways. Generated by automation algorithm, voltage control, switch sequence, then protection strips initiated by the operator locally using the control facilities of the bay devices, receive from the substation control level via the communication. I will see the historical representation of the network control center and its historical development. The substation control level provides an interactive workplace for the operator with control and visualization elements. Here, the scheme of whole substation is available. Events are signaled and measurements can be monitored. It is possible to control all parts of the substation. The substation interlocking extends the bay interlocking from higher point of view. For example, an isolator can be operated if the related circuit breaker is switched on, but the topology of the substation scheme shows that there is no current. The substation control levels provides communication interface to the network, control center, and if requested to further network service providers like asset and maintenance management, network planning or protection supervision. Not all available data is communicated between all of the levels. Instead, the information exchange has to be engineered. The network control center observes and controls all substation of the network. Furthermore, the power in feed of the connected power station and the power exchange with neighboring power stations are managed on this level. The transmission system operators build the control area in the territory of their network, control the reserve power availability and ensure in this way the frequency of availability. The network control centers provide several workplace with screen and keyboards. An overview of the overall power system is provided on the large wall displays. If you see the historical development, the digital protection and control system of the substation were developed and widely introduced during the last 3 decades. This system brought about a fundamental change in the technology and operation philosophically. These advanced digital technologies are currently applied in 100% of the important UHV, EHV, HV substations in the progressive industrial countries. The substation control technology was stable and remained unchanged for about 100 years from the beginning of the electric supply since the 1990s. The board wall of the substation was filled with electromechanical controls and measurement elements representing the substation schemes. Figure demonstrate this situation showing a view of substation control wall from the 1920 and 1985. The protection technology has also changed within the last few decades from the electromechanical relay scheme completed on panel to analogous protection cubicles to digital protection device and intelligent electronic devices as shown in figure. The protection cannot avoid disturbances but minimizes the consequences through rapid, secure and selective disconnection of the faulty equipment, automatic reclosing for supply recovery in case of transient failures, logging and recording the disturbance and supporting a fast network recovery. To perform this task, the former protection panels were equipped with the several devices connected by the complex wiring logic. The analog electronic technology applied electronic boards and an electric bus to perform the logical links. Both technologies were installed in a special relay room of the substation building. Consequently, all signals were transferred via cables between the relay room and the switch base with some disadvantages as considered for the control. The digital protection and control technology, which was developed in early 1980s, brought about a technical revolution and the deep paradigm change. Today, each switch bay is equipped directly with protection and control IDs, which are based on the identical technologies in hardware and software. Now let's look at the modern architecture of substation. The control scheme wall have also been replaced by industrial computers offering an Ethernet interface or communication with the bay IDs as shown in figure 11. That is in this particular figure with the help of IDs. The screen of ICs displays the overall substation scheme and offers the selection of large amount of detailed scheme, various event logs, diagram, measurement and fault recorders. Video observation and others. The flag relays for the recognition of the events are not more applied. The monitoring comfort is fundamentally improved. For example, all event messages and changes of measured values are represented with the timestamp. As a rule, the time resolution of 1 millisecond is applied. The control is possible using a simplified keyboard by cursor to select the device to the control and by simultaneously pressing two separate keys, command and confirm. The IC provides one or more link to WAMs for communication with the network center and further service departments of the network operator as shown in figure. The application of international communication standard ensures the interoperability of network control centers and the substation automation system from different vendors. In the same way, the bay related IDs of different vendors may be integrated into substation automation system. As a rule, the protection and control scheme of UHV, EHV, and EHV substations A contains main protection, backup protection, and bay control device. The main protection principle applies are presented in the table, and principle of the protection functions are described ahead. The differential protection principle offers the highest selectivity. Therefore, it is often used for the main protection of EHV and HV lines. The protection function is based on the fact that along a fault free line, the ingoing current should be equal to the outgoing current. However, the current flow along with the line will be influenced by the capacitive current. Therefore, the difference of the ingoing current I1 and the outgoing current I2 of the fault free line is not exactly equal to 0. A small difference will be measured for unfaulted lines. A stabilizing current is introduced to avoid an over-functioning of the differential protection. The protected network assets are basically line feeders, bus bars, and the transformers. The differential protection scheme. This principle offers the higher selectivity. Therefore, it is often used for the main protection of EHV and HV lines. The protection function is based on the fact that along with a fault-free line, the ongoing current should be equal to the outgoing current. Now here in this figure it is shown this principle. The current flow along with the line will be influenced by the capacitive currents. Therefore, the difference of incoming and outgoing current is not exactly 0. A small difference will be measured for unfaulted lines. A stabilizing current is introduced for that to avoid the over-functioning of the differential protection. Now, the differential protection has a disadvantage that the protection selectivity is strictly limited to a zone between current transformers. A backup protection cannot be performed with this limitation. Therefore, a differential protection is mostly combined with the distance protection for the backup. Now let's understand the distance protection principle. The distance protection continuously calculates the impedance using the instantaneous measurement of the voltage and current. If a short circuit occurs along the line, the voltage declines and the current grows. The impedance will be significantly reduced. The impedance is measured of the distance of a fault. Several impedance zones can be parameterized to ensure both the selectivity and the backup protection features. Now, here in this figure, it demonstrates the distance protection principle. Now, this figure demonstrates the grading principle of the distance protection and the protection zone of the line differential protection. The differential protection units in the substation A and B mutually communicate the sample values in the real time. However, the differential protection cannot recognize faults between the busbar and the access point of the current transformer. The sections are protected by the distance protection. Distance zone 1 is operated with either a small or no time delay. To avoid wrong trips, each of the distance protection covers 80 to 90% of the line impedances. The reach of zone 2 exceeds the line length and the trip after higher time delay T2 and zone 3 may overcome the next bus bar C with the time delay T3. The same principle is applied for the protection of substation B. A fault in location 1 can be tripped by the distance protection ZA1 in zone 1, and the fault in location 2 can be tripped by the distance protection ZB in zone 1. But this would be only a rapid trip of one side of the line, and the short circuit could only be finally tripped after the time delay of zone 2. To avoid such an extension of a fault duration, the principle of teleprotection is applied. Both protection units submit the pickup to the opposite device by communication link. If one of the devices detects the fault location within zone 1, both devices trip in the same time. Furthermore, the backup protection for line B C is performed by the distance zone 2 and 3 of the protection in substation A. In HV line protection scheme, the directional overcurrent principle is often used for backup protection combined with the main distance protection. The overcurrent protection principle is based on the simple criteria: the increased current in case of fault as demonstration in the figure. The overcurrent protection has to trip the circuit breaker as faster as higher the short circuit is. Following this principle, two methods are applied. The definite time overcurrent protection trips with the definite time delay if definite overcurrent I is exceeded. Extremely high short circuit current I are tripped without or with the limited minimum delay. The inverse time overcurrent protection trips in accordance with the time delay depending on the short circuit current for the application of meshed HV networks. The overcurrent protection is supplemented by the specific directional criteria and needs the input of the phase voltage or for processing. The busbars are the most sensitive components in the network. A busbar fault may cause a trip of the whole or the part of the substation with all connected transformers and lines. The sum of complex current considering the direction results in difference current that will be strictly calculated separately for all electric autonomous busbar segments. In case of the busbar segment fault, all circuit breakers of the connected feeders will be tripped. The busbar protection shall decide to trip within 8 to 12 milliseconds to avoid equipment damage. Switch operations have to be performed as quickly as possible after the faulty busbar is tripped for connecting the affected feeders to the healthy busbar segment. The busbar protection is configured as a system with digital bay units and one central IED presentation as shown in here in figure. Both components of the system are based on the identical technology. Now let's understand the transformer protection scheme. The bay IEDs continuously submit the measured instantaneous currents and the position of the isolators to the central unit. The central unit detects the busbar segments and the appearance of the fault. If fault detection is definitely recognized, all feeders connected to the faulty segment are tripped without any time delay. The backup protection of the busbar is performed by the protection system of the feeder connected to the faulty busbar segment. The typical transformer protection scheme is presented here in this figure. In general, the transformer differential protection principle is identical with the line differential protection. The differences consist of the following: adaptation of the measured current in the accordance with the transformer ratio, direct measurement of the different currents in one IED, no need for blocking over functions in accordance with the interest current. The Buchholz protection is also the part of the transformer delivery. It monitors the gas stream between the main oil tank and the oil extension container of the transformer. The gas stream detects an internal fault and, depending on the stream intensity, either an alarm or an instantaneous trip are performed. The backup protection is often the overcurrent protection. Also, the distance protection is applied. The transformer protection scheme has to consider the number of windings and the connection scheme. The variety of connections is present into the figure. The digital IEDs for control and protection also contains further protection and protection related functions. Now figure here gives an example of the often applied functions for 110 kV feeder with resonant neutral grounding. The resonant neutral grounding is partially used in HV networks. However, the majority of HV network uses the solid grounding principle, which is the only method applied for neutral grounding in EHV networks. The scheme uses the differential protection as the main protection. The backup protection is performed by a combined protection and control device using the distance protection as basic protection function. Supplement protection and protection related functions are enabled. The identification numbers according to the American National Institute are applied. The ANSI systematic assigns number to the different functions and it is globally known and accepted. The protection engineer mutually consider protection aspect using the ANSI ID numbers instead of principal names. The additional functions applied are defined as follows. The automatic reclosing function is mainly used in network with overhead lines. Here, the experience shows that about 85% of the faults are temporary in nature caused by atmospheric lightning, wind and phase conductor swing, tree contact, birds. The external influence generates an electric arc which shorts the affected phases. The fault disappears when the protection trip interrupts the energy feeding the arcs. This means that the line can be switched on again. The reconnection is accomplished after the dead time that the air can be deionized. As the name suggests, the overvoltage protection has the task of protecting electrical equipment against overvoltages. Overvoltages may occur on long, low-loaded transmission lines, generating an excess of reactive power. The overvoltages may causes, for example, insulation problems and damages. The lack of synchronism function provides the synchronization check before connecting two sections of the network, for example, a feeder and bus bar or a bus bar and a power station. The synchro check evaluates the differences of the voltage magnitude of both sections, delta V, the angle between the voltage and delta D, and the frequencies delta F. This method diversifies that the switching does not endanger the stability of the network and is also used in combination with the auto-reclosing. Resonant neutral grounding is partially used in 110 kV network. In these networks, the shorting of one phase to ground does not generate high currents. In this figure, the benefits of communication interface of ID is also demonstrated. Here, ID communication interface are used for teleprotection, for external regarding protection data or parameter setting, and for the link to substation control place. The philosophy of the protection and control scheme for HV and higher voltage level switch base strictly requires the installation of separate and autonomous devices for the main, the backup, and the breaker failure protection. It is often required that the device come from different vendors. That means they are also independent regarding the DC power supply. So here, friends, we have studied and discussed the smart substation, the feeder automation, then monitoring and the protection and the control in this module. So these are the assignment questions for you on your screen. And thanks for listening. If you have any query, you can write to me on somnath.hadpe@yahoo.in. Thank you.